Greetings, students. This is Mr. Allen here. Today we are going to look at section 7.4, which is on trigonometric substitution. We have two objectives today, but I'll be honest, we're going to mainly focus on the first one, which is using trigonometric substitution to solve integrals. So this lesson is actually a really cool lesson. It's something that when I first learned about this, I kind of thought it seemed like you were almost working against yourself. It almost seemed like cheating somehow, but it's just amazing that it works. I think that substitution may be the most powerful tool in all of mathematics. Anyways, so when are we going to want to use trigonometric substitution? You want to use trigonometric substitution anytime you have an integral. I shouldn't say anytime. You might want to use trigonometric substitution if you have an integral that involves anything of this form. So for example, if you had an integral that had the square root of 4 minus, let's say, 9x squared, and I'm still on highlighter there, sorry about that. That would be an instance when you want to try to use trig substitution. So what I'd like you to notice is that this a squared minus u squared, and by the way, a is a constant, u is a variable term, looks very similar to this constant minus this variable term squared, doesn't it? And this here looks very similar to this because I have a constant squared plus a variable term squared, and then finally this looks like a variable thing squared minus a constant thing squared. So let me show you just a real quick example of that. So let's say I had something like the square root of a squared minus u squared. So if we go back to this previous slide, that's this situation here, which means we're going to use this right here. In other words, we want to let that x term, the variable term, equal sine theta. So in this case, I didn't tell you what a was. A could be 9 or 5 or whatever, but we're going to let u equal a sine theta. So watch what happens. We're going to let a just be a, so it's a squared minus, and now instead of u squared, this is u squared to be a squared sine squared theta. Now you'll notice that both of these terms have an a squared in them, so they can be factored out to the front. And then of course 1 minus sine squared theta, well, we know that's going to be cosine squared theta by the Pythagorean trigonometric identity. And of course, now we've got the square root of some things that are squared, so it's simply a cosine theta. In other words, what I'm trying to show you here is if you have an integral that has something like this square root in there, you can actually convert this square root to something that doesn't involve any square roots. And you can actually find the antiderivative of cosine very easily. So it actually, even though it seems counterproductive, you're actually making less work for yourself. This is the most important slide. This has all of the reference information that you need. If you have something of this form right here, you want to use sine. And again, that's going to go back to the fact that cosine squared theta is equal to 1 minus sine squared theta. And if you look carefully under the square root, you'll see that there's a constant squared minus a variable term squared. If I have a squared theta plus u squared theta, you're going to use a tangent. And if you have u squared minus a squared, then you could use secant. Now let me just focus on, let's focus on this first one here that involves sine, which is probably the easiest for students to understand. So here's our theta. Remember, sine is opposite over hypotenuse. So the sine of theta is u over a. And by the way, if you multiply a over the other side, you would get u equals a sine theta. So that should kind of make sense. U is equal to a sine theta. Now let's talk about this third side here. How would you get that third side, which is a leg? Well, you could use the Pythagorean theorem. So a squared plus b squared equals c squared. And you will find that that third side is the square root of a squared minus u squared. If you have a problem that involves this, If we draw the reference triangle, here we're going to talk about arctan. Remember, tangent is opposite over adjacent. And then we can do the Pythagorean theorem to get the third side. Anyways, you need to kind of familiarize yourself with this table and then practice with these. And I think it'll make sense after you do a few. Let me show you an example. Now, this first example, I have all the work typed out already, so it looks nice, so you don't have to try to understand my handwriting. And then the second example I do, I'm actually going to work it out by hand, so I'm apologizing in advance for my handwriting. I just thought it might be nice for you guys to see me actually working on the problem instead of just having it already like pre-written out. Okay, so I want to integrate this. Notice that this problem looks like square root of a squared minus u squared. That's right here underneath the square root symbol. So what we're going to do is the following. We are going to let x, that's this guy here, equal 3 sine theta. Now, hopefully you understand that the 3 is because the square root of 9 is 3. So x is going to be 3 sine theta. Now, what I recommend you do before you actually try to integrate this now is we've got to figure out what these other values are going to be in this problem. So again, we've already established that x is going to be 3 sine theta. So if I do the derivative of that, then we can clearly, well, I guess I should say clearly, but hopefully see that dx is going to be 3 cosine d theta. So that's going to give us this piece, okay? And then the next part, in fact, let me, yeah, we'll leave that alone. So the square root of 9 minus x squared is 3 cosine theta. So that's what I'm going to put in here. Now, in case you're not sure where all that comes from, let me take a minute to go to that reference triangle here that I mentioned a second ago on the previous slide. If we're dealing with sine, and that's what we did, we said that x is going to be sine. Remember, sine is opposite over hypotenuse. So you can clearly see that sine of theta, which I have written right here, would be x over 3. And then if you multiply both sides by 3, you can see where I get this. So that's wonderful. How do I get this third side? Well, you would do the Pythagorean theorem, and that's where you'll get your 9 minus x squared. That's going to be 3 cosine theta. Now, in case you're like, Mr. Allen, I don't understand where that's coming from, let me show it to you where that's coming from, okay? So what is x? I think we said that x is going to be 3 sine theta, and we're squaring this, right? Okay, so this is going to be 9 minus 9 sine squared theta. Okay. All right, so then I can factor out a 9. I'm going to get 1 minus sine squared theta. What's 1 minus sine squared theta? Well, that is cosine squared theta. So I've got the square root of 3 squared times cosine squared theta. And what is the square root of that? Well, it's 3 cosine theta. That's what we said just right there. Okay. Now, if you draw your reference triangle, after a while, you'll get to do it really quick. But if you're not sure where this comes from, this isn't just magic. There is a reason. Now, I'm going to clear all the stuff I've written on this slide, unfortunately, guys. I'm sorry. All right, and then this last piece here. Remember, we know we were given that x was sine theta, right? Well, if you look back at our original integral, we had this x squared here. It'd be nice to know what x squared is. Well, if we square both sides, oops, this was 3 sine theta. So that'd be 9 squared. Anyways, so now I have everything that I need to plug into my formula. So let's go ahead and do that now. And I'm going to try to highlight this here. So what do I put in for, actually, nix what I just said there. What am I going to put in for the square root of 9 minus x squared? Well, that's what we said right here, okay? What am I going to put in for x squared? Oh, that's what we said over here. What am I going to put in for, let's go with blue. What am I going to put in for dx? Oh, that's what we said right here. So all of those things have been plugged in. So we went from this algebraic integral to this trigonometric integral. Now the good news is now that we've got this written in this way, guess what happens to the 3 cosine theta and this 3 cosine theta? Cancels. Of course, we can pull this 9 out to the front, make it 1/9. And what is 1 over sine squared theta? Well, that's cosecant squared theta. What is the antiderivative of cosecant squared theta? Well, cotangent theta, negative cotangent theta. So then I got negative 1/9 cotangent theta plus c. Now you might be tempted to stop there, but let me just tell you, you are not done yet. You are not done yet because remember our original problem was in terms of theta. Was in terms of x. And here we just got our antiderivative, which is in terms of theta. So we need to go ahead and convert this back. Now I'm going to show you how to do that. We need to know what cotangent is. Remember, this is theta. Cotangent is adjacent over opposite. So I'm telling you that the cotangent of theta would be the square root of 9 minus x squared all divided by x. So this substitution right here is I've substituted the cotangent theta back in. And then of course here we have our final answer, which is negative square root of 9 minus x squared over 9x plus c. So again, it's pretty miraculous. I think this is one of the coolest sections. This is something that I'll be honest, I don't think I would have ever thought of this. I'm not really sure who the mathematician was that came up with that, but it's really good. So hear the vacuum cleaner there. I hope that's not too loud. They're vacuuming out in the home. Okay. I'm going to skip this slide. I'm going to tell you, first of all, you do not need to memorize. You can use it for reference. I just spelled memorize wrong. I spelled remote. Memorize. You do not have to memorize this. Okay. Anyways, what I'm trying to say here is if you needed to integrate anything that looks like one of these, here's the rules for doing it. This is not something, though, that I'm asking you to memorize. So, for example, on number 3, if you had something like the square root of, let's see here, 16x squared plus 9 dx, you would simply, in this case, you would know that u is the square root of 16x squared, so that'd be 4x. A would be the square root of 9, which would be 3. And you would just plug all those values into this integral, and that would give you the answer. Okay? All right, I want to do one more example of this trig substitution. This one's going to involve tangent and secant, and that's based on this here. Now, what I would encourage you to do is stop right now, stop this video, and draw that reference triangle I talked about. Okay, I'm going to just go ahead and go forward and pretend that you know what that is. But here we go. So first thing we want to do is we want to recognize, since this is 1 plus x squared, that's like a squared plus u squared. So that's we're going to let x equal the tangent of theta. If x is the tangent of theta, then dx is going to be the secant squared of theta d theta. Okay, so now we want to try to figure out what this square root thing's going to be, okay? So if I had plugged this x, which is tangent theta, if you plug tangent theta in there and worked it out like I did on that previous example, hopefully you can understand now why that's secant theta. And then, of course, and you might ask, why do I want to know what x to the third is? Well, I want to know what x to the third is because of this stuff on the top. And I know what x is, so I just cube both sides, and I know that x cubed is equal to tangent theta. So now I can go ahead and substitute in all the things that I need to do. Let's go ahead and do that. I'm going to try to write as neatly as possible, guys, but I'm going to apologize. My handwriting isn't the best. So this is going to become the integral, and I'm going to pull out the 9 to the front. X cubed, well, we just established what x cubed is. It is tangent cubed theta over, and what are we going to put in for the square root of x squared? Well, that's going to be secant theta. Now, don't forget, this is a crucial step. In fact, let me make it a different color. What do we put in for dx? We are doing u sub, so we have to appropriately change dx. Dx in this case is going to be secant squared theta d theta. All right, now good news, stuff cancels. One of these secant thetas cancels this secant theta down here. So that gives us the following. 9 integral of tangent squared theta, and then let me write this in a slightly different color. I'm being a little triggy here. And I'm going to write another factor of, and by the way, you'd agree that tangent squared theta and tangent theta are tangent cube theta. And then I still have one factor of secant theta d theta. Now I've done this on purpose because I want you to recognize something. Actually, let me do one more step and then we'll see if you can recognize it even more clearly. 9 integral, what is tangent squared theta? Tangent squared theta is secant squared theta minus 1. And then I'll leave this other stuff in green. Tangent theta secant theta d theta. Can you kind of guess why I'm doing this? Well, I hope it's feeling like a little bit of deja vu right now, because we're very quickly, oops, not 7.3, 7.4, but 7.3. We're going back to the last section, 7.3 on trig integration. So now we've got this, and now let's go ahead and distribute. I'm probably going to run out of room on this particular slide, and that's okay. So I'm going to make this 9 integral, and so then this is going to be the secant, the secant squared theta, and then I'll write it in green. Tangent theta secant theta d theta, and let's keep going in red again, and then minus, and then I'm going to have integral of tangent theta secant theta d theta. I'm running out of room, and I need to make sure I don't forget my brackets here. This whole thing has to be multiplied by 9. Now, why I'm doing this now is I'm hoping that you're recognizing that the derivative of secant theta is tangent theta secant theta d theta. So now I can do a u sub, if you will, where u is secant theta, okay? And then du would be, this is d, oh, that's right. And then the derivative of that would be tangent theta secant theta d theta. Okay, so let's go ahead and we're going to go to the next slide. But before I do that, I want you to try to think about, so this is this secant squared theta is u. In fact, let's just go to the next slide. So this is basically going to become 9 times the integral of u squared du, and then I think it was minus the integral, and this is going to be a 9 as well, of du, where u is that secant theta. So this is going to become 9u to the third over 3, and then minus 9u, and then plus c. But don't forget now that u was, remember, u was secant theta. And so we're going to end up with 3 secant cubed theta minus 9 secant theta plus c. Are we done yet? The answer is no, we are not done yet, because we have to remember that our original problem was not in terms of trig stuff. So now we need to use all of this information that we have here, and we will get our final answer. In fact, here, let's go ahead and factor out a common factor of 3, and then secant theta, which is going to give us secant squared theta minus 9. Oops. Minus 3, sorry, that would be 3, because we factored out a 3. So that'd be 3, parenthesis plus c, and our final answer, and I'll go back to red, now I'm going to substitute back in, and our final answer will be 3 square root of 1 plus x squared times x squared minus 3 plus c. Woo! Oops, that's going to actually be minus 2, right? Because remember, secant squared theta right here, where we have secant squared theta, if we square both sides here, that's going to be x squared plus 1. And so then we got this -3 there. So that'd just be a -2, not -3. I think we're done. Oh, that was a tough one. So anyways, I thought I'd show you kind of a harder one. That's all, guys. Thanks for your attention.